Hey, what's up guys, my name is Cherno. Welcome back to my code review series. Yes, it is that time of month yet again where you guys send me your code and I take a look at it. So how I usually pick these is just based on if I think there will be some value for you guys. Now a couple episodes ago we actually took a look at a ray tracing example. I'll have that video linked up there if you want to check it out, because today we are yet again going to be taking a look at ray tracing, specifically an implementation of something called ray tracing in a weekend. I mentioned this last time in that ray tracing video. For those of you who don't know, it's basically like a little website book thing that teaches you like ray tracing in a weekend. That's kind of the idea. Now I did mention that I would probably take a seat at some point and do my own kind of ray tracing in a weekend. That is, implement like the ray tracing in a weekend, try and improve it and make it kind of like an educational video series. I am still planning to do that, but when I opened up my emails today, what I saw, the very first thing I saw actually, this is literally the most recent email there, is ray tracing in a weekend with IMGUI and multi-threading in C++ 17. And I thought you guys would enjoy taking a look at this as well. So let's take a look at this. This is from Valerio Format. I'm expecting his code to be well formatted. Yeah, that's pretty cool. Cherno, nice joke, Cherno. Hi, Cherno. I'm a longtime fan of the channel, while cursing time zones prevent me from watching most of your Twitch streams from Italy. Oh, from Italy. I don't think we've had an Italian on the Cherno review series or the code review series just yet. Last weekend, I had some time on my hands. I decided to try to follow the ray tracing weekend book. Yeah, I will have that linked, by the way, in the description below, the ray tracing in the weekend thing. Highly recommend you check it out if you are interested in graphics. I have to say I had a blast. See, Valerio certainly had a blast, so yeah. 35 years old physicist, and while I'm not a professional coder, I've been working daily in C++ for over 10 years. Maybe this technically means I'm a coder nevertheless. But only recently I have become interested in learning advanced and more modern C++, so I take every chance I get to practice. I tried implementing the book, following my own style wherever I could, and as a bonus I've also thrown in some multi-threading just for fun. I know you're feeling on projects that don't build out of the box, guys watch the series, so I've taken extra care to take care of the dependencies either by submodules, by letting CMFA. That's good. That's good. I'm expecting a 35-year-old physicist who's been working in C++ daily for over 10 years to get this right, so fingers crossed. He has a CMake project, but it was created by Visual Studio. Sure, I mean, I don't mind CMake projects, so it should work out of the box. If you want to take a look at it, I would be immensely honored. You can find the code at this, and I will have this repository linked in the description below as well. Keep up the good work, Valerio Formato. The only thing I found puzzling during this build is the linker was able to find the D3, D11 libraries out of the box. I guess they're already in some default link path. Yeah, if you install Visual Studio with like the kind of DirectX SDK, which is usually included as part of like some C++ for games distribution or whatever, I think it's just included in the kind of standard Visual Studio like MSVC library, so that would explain why that is there. A few things that I like about this, by the way, and why I've selected it for this video, is because this is a person who is 35 years old, not 13. And I think that just the age of the person can have a lot to do with what the code is like. Now, not necessarily, I don't want to be like ageist or something here and say that, yeah, all 35-year-olds are better than 13-year-olds no matter how much experience they've had. That's not true at all. But I think that maybe we'll see some differences in the code compared to someone who might be a little bit younger, just because that life experience, I think, actually teaches you to be a better programmer, believe it or not. Working daily in C++ for over 10 years, interested in learning advanced and more modern C++, I tried to implement the book following my own style, and as a bonus also thrown in some multi-threading. So these are all kind of things that I think will make the code interesting to look at. Hopefully we can take a look at a more modern C++ example by someone who hopefully knows what they're doing, and I think we're gonna have a really good time with this one. But first, I want to mention that this video is sponsored by Skillshare. Skillshare has pretty much sponsored the entire code review series this year, so let's just start off by giving them a huge thank you. For those of you who don't know what Skillshare is an amazing online learning community where millions of creative and curious people from all around the world can come together into one place to learn a new skill or skills, because there's a lot of stuff on that platform. Literally like any topic you're interested in, such as illustration, how to draw better, photography, videography, how to make better YouTube videos, how to start on YouTube, marketing, productivity, all of that stuff. Skillshare literally has thousands of classes to choose from, and they have an absolutely amazing amazingly large and high quality library available for you to check out. And these videos are very efficient. They're not like long, they're not YouTube kind of, you know, don't forget to hit subscribe and I need my watch time. No, they're concise, they're to the point, they're efficient, and they're gonna teach you those new skills well. And personally, that's one of my favorite things about the platform, the fact that it's just so efficient at teaching. Skillshare is offering the first 1,000 people who click the link in the description below a 1-month free trial of Skillshare, where you'll be able to check out their entire range of classes for free for a month. So definitely give it a go and sign up using that link. I'm sure you guys will find something there that you are interested in. Yeah, it's just a great platform really. Thanks to Skillshare for sponsoring this video. All right, Valerio the physicist, let's see what you've got. So he mentioned that he would have a good build process, and what do you know? It works. Color me impressed. Okay, so we just have this it kind of weirdly fades out. I've clicked somewhere and now this is dead. Okay, maybe things aren't going as smoothly as I hoped. Let's hit start and see what happens. My, that is slow. Why is it so slow? It's rendering nothing. We're gonna see something? Oh, some spheres maybe? Why is this so slow? And it's using 100% of my CPU cores. So it's using like all 32 threads are occupied here. And it's running this slowly, rendering a few spheres. Okay, something's very wrong here. Well, he certainly wasn't lying about the multi-threading, that we can definitely see. But I'm just... By the way, this is running in release mode, just in case you guys think I'm a fool. Okay, we're going to come back to the performance. This might be a little performance episode, would be in line with Optimization October, even though it's like December now. Let's take a look at the code and we will definitely circle back to that performance because I am almost 100% sure that I can make it faster. Okay, so we initialize this app. Pretty standard stuff here. Let's see what this does. So he is using DirectX 11 in some way, possibly just for like the IMGUI rendering and the actual presentation. I assume all of the ray tracing is done CPU side, certainly with that performance and that like core usage that we looked at. Let's take a look at this stuff. So he's using no discard, which is a cool little attribute. It basically tries to prevent us from discarding the result of this function so that we don't kind of call it as if it was a void function, which is fine, throws a compiler warning. Overall, I like the neatness of the code. I like the M underscores for all of the private members here. Looks good to me. Obviously very Win32 dependent. You've got some DirectX backend stuff, all pretty kind of boilerplate. I probably won't spend too much time looking at like all of the DirectX 11 stuff because this is all just boilerplate code to like create like the device and the swap chain and all the context kind of stuff. Update texture 2D. That is probably what I expect is actually rendering onto the screen, which again is pretty standard. We're just mapping the memory there and then doing a mem copy from the image buffer, which is where I assume the ray tracing is writing into. So we have like a CPU side image buffer over here, which is wrapped inside a unique pointer. Interesting. I probably wouldn't have done it this way. I'm not a huge fan of like wrapping, because what this actually is, if we take a look at where it was created, which I assume is maybe, okay, it looks like it happens over here, create image buffer, and then you're really just doing an allocation of just raw memory like this. I would probably make this like a vector so that you could basically have like an array that is the size that you need, but on the heap. If you're doing it that way, I don't know, I just don't like the idea of wrapping it in unique pointer, having a raw array wrapped in a unique pointer. You could of course just, yeah, Clang format, that's cool, using Clang format, pretty nice. You could just obviously have something like your image buffer as a raw buffer like this, and then you could allocate it. I may have done it that way. In Hazel, we have like a class called buffer, which basically wraps exactly this and has a lot of like convenience functions and all of that. It doesn't own the buffer of memory, so it won't delete it if that stack object goes out of scope or anything, but it is like a wrapper over that raw pointer to make things a little bit safer and easier. But I don't know, unique pointer for a array, basically for a raw kind of allocated array. What do you guys think about that? Leave a comment below. I probably wouldn't do it, as I mentioned. I would make this like a vector of UN8T or something like that, and then resize it to the appropriate size, or maybe use a raw pointer like this. Okay, so we figured out where the image buffer is. The renderer, I'm assuming, this is our big boy who'll do all of the work. So let's take a look at the renderer class. So we have a bunch of render states, ready, running, finished, stopped. I'm assuming some of these are probably necessary for like multi-threading and maybe also figuring out like when to update the image and all of that, if it's still running or not. Set samples per pixel and 500. Okay, well maybe that's why it's slow. Let's try something a bit more reasonable like 32. Max ray depth 50. Ray depth bounces. 50 bounces? My gosh. Let's make this like 8 or something. Let's try it again with these settings. We'll see how much this speeds up, and then maybe we'll actually see an image. Okay, so let's hit start now. Okay, that's faster. But when it gets to the spheres, it's still quite slow. Why is this taking so long? Okay, so a few notes about ray tracing and all that. I haven't actually looked at the ray tracing in a weekend code. I don't see why it would be this slow. I mean, when it gets to like all the bounces and there's multiple intersections, because you can see the reflection of the spheres here, I would expect it to be slower, but this is insanely slow. And for some reason, I doubt that it's the ray tracing in a weekend code. So maybe you've done something weird. I'm this close to just dropping this code review and turning this video into like an optimization video. Should we wait for this to complete? There's a fair few spheres around, which is nice. So the image obviously looks quite noisy because we made the samples so low. One thing I'd recommend though is maybe add a denoiser to this. I mean, I'm assuming there's not a denoiser once this finishes. I just don't have the patience to wait for this, I think. You know what? Let's do it. I'm going to wait for this to finish rendering. We'll see how long it takes to render. Then we'll see if we can do better by trying to optimize it. One thing I might do really quickly is actually stop this from taking over all of the threads because I need some like cores available to record this video. So let me just quickly go into, let's see, the renderer. How does this render stuff? We might as well look at this. So renderer render, that was a good bet. Start rendering, render state is set to running. What do we have here? We have a lambda. We're going through this, right pixel to buffer. Okay, right pixel to buffer pixel coordinates. So it looks like we're writing pixels one by one, but I assume this is spread across over all the cores. Yep. We have a thread pool. We add literally every single pixel from image size y minus 1. So that I guess is the top. And then we go from the top to the bottom instead of bottom to top, I guess, which is why I've got this reverse loop. And then we go through every horizontal pixel, as you saw there, and we add this to thread pool. This, I guess, is the single-threaded version of this versus adding a task per pixel. I'm not sure if I would separate every pixel into a task, but it is a thread pool, which obviously makes me assume you haven't made 100,000 threads. So how do you make the thread pool? So thread pool just starts off. There's the pool. Construct max. Okay, thread count. So are we using this, or we're using just whatever's available? I'm not sure which. Well, I guess you were using the default constructor. Let's just halve this so that we use maybe half of the cores. This will obviously slow it down, but it will mean that I can hopefully record the video as well. Now that I think about it, I hope that those sections when I was running it with all the cores actually recorded. Okay, to be honest, this doesn't even look like it's slowed it down that much, but we should now be utilizing half of this stuff. So you can see our usage is like 78%, 77%. It's not 100%. So we're obviously not occupying everything with this ray tracing app. Cool. All right. Well, let's just run this for a while, see how long it takes. And I hope you print out the time that it took. Let me just quickly check that out. Okay. Logger debug rendering took, and then you've got a stop time minus start time. Okay, good. So in other words, we should actually see how long this takes when it's done. Whenever that is. Okay, it's done. 455 seconds. That's 7.5 minutes to render this frame at 32 samples with all this noise at this resolution, which is what, like 1280 by 720. I think I could have written a ray tracer in that time. All right, guys, throw this code review out the window. We're gonna fix this. Back at it again with Cherno fixes your code. Okay, so again, I don't know what is going on here, but I just know from experience that that is way too long. So there has to be something wrong here. So let's talk about how we might approach optimizing this. What I'm gonna do is just a really quick scan over the code. First of all, there is not that much stuff going on. You know, there's like a ray tracer is mostly just mathematical functions like normalize, square root, reflect. You know, that's really all there is to a ray tracer. There should not be anything else really going on apart from the mathematics. And I think it's really, really important that you don't try and over-engineer the language side of things, because that's really easy to do. You could get lost with all of C++'s features. He did mention he was using C++17. He gave his own personal style to this, whatever that means. We're about to find out what that means. But my initial fear is that something here is slightly over-engineered, because the physical mathematics here, I don't think that it's possible for the actual mathematics that need to be done to take that long. Like, I would expect that frame to Well, definitely not over a minute. Like, that is wild. So let's take a look at what's going on here. Okay, so dielectric scatter, and that is what? This is a material, dielectric. Okay, so we have dielectric materials, public material. Okay, so the first thing that I'm not really potentially liking here is the whole virtual function class hierarchy situation. Why is that an issue for performance? Because the problem is that I'm sure that he's got a bunch of different materials. Let's see what else is here. Metal, Lambertian as well, scatter, and they've all got scatter functions. So per pixel immediately when we look up a material, it's not as simple as just deciding what it is we need to do. We need to also make sure that we dynamically dispatch that to the right function using a vtable. Now again, fundamentally not the slowest thing in the world. However, when you're writing a ray tracer, you have to realize that you are processing each and every pixel one by one. Whether that be across different cores, I don't care. You're still going through each and every pixel on the CPU, and you're running some kind of code over that. To make matters worse, what happens when the ray bounces? Well, you have to cast another ray somewhere else. So potentially multiple bounces, obviously per pixel. I think we're doing like 8. There could be other stuff going on, such as lights and shadows. Like, there is a lot of stuff that happens. Like, these functions are very hot in the sense that they get called so much. And because they get called so much, we need to be careful with things like memory layout and like what it is we actually do per pixel, because that's really, really important. And so immediately, I don't like the whole dynamic dispatch I don't like the whole like inheritance vtable situation here, because that is definitely going to be slowing things down at this scale. Now, you've also got an optional here, which isn't the worst thing in the world, but probably will require some additional processing at some point. I could imagine some cycles being wasted there. The other big problem, by the way, with having virtual kind of classes like this and the whole vtable thing is that you kind of can't really have them be tightly packed in memory anymore. Like, they become, and we'll see in a minute, I might be wrong, but I'm pretty sure this means that you're also heap allocating each and every one of these materials, which again, I think for a material is fine. But yeah, let's see what the sphere situation is, because that looks like your only object here. You've got a hittable object list, which has a hit function, hittable object, and a sphere. Maybe a sphere is a hittable object, and then you do hit on that. So where does that get called from? Hit object, hittable object list, hit, and then this is all of the objects probably in the scene. So we have a scene filled with objects, and then we run hit on it, shoot ray. So we shoot a ray out per bounce as well, and then we try and call that hit function, which will obviously go through all of the objects, which are all spheres, all on the heap, all somewhere else in memory, and then try and figure out if it hits them or not. So from a memory kind of fragmentation CPU cache situation, this is far from ideal. And I think, again, at this scale, that matters so much. And I'm probably about to prove it to you, to be honest. But we'll see. Let's not get ahead of ourselves. So I think I kind of understand how this works. I just want to look at the renderer one more time. So when we do the renderer, so what we do is we go through and we use SCD accumulate, which again goes through begin and end samples, which we have samples per pixel. So we have basically 32 of these that we've made initialized to 0. That's not too bad. We're running over 32 of these. But then we go through and then we shoot rays, which if it hits something, we use the material. So we look up the material to see how we should basically scatter that ray, how we should proceed with that ray. And then we run shoot ray again, and we use scene.hit. And scene, what's scene? Scene is a hittable object, which is probably that hittable objects list. How do we add stuff? Scenes.cpp, that's useful. How do we add stuff to the scene here? So if we're a default scene, then we take scene, and mscene is a hittable object list. Okay, so we have that scene, and then we add, and yeah, you can see all of these spheres are make shared, right? You're using a lot of heap allocated memory here. Every sphere is somewhere else in memory. I would not do this. what I would do is I would prioritize as much as possible to try and keep this scene as cache coherent as possible. I want it to be in contiguous memory right next to each other. I want these to be stack allocated objects, right? This hittable object list should not contain a vector of shared pointers. It should contain a vector of these actual hittable objects, which again might be difficult because they're all kind of virtual and very object oriented. So you have to remember, with ray tracing, with these mathematical algorithms, you need to prioritize the math and the data. That is all that needs to be calculated. You are basically getting your CPU to do a bunch of mathematical calculations. They should be as streamlined as physically possible. They should not be spread across memory like this. So I'm not sure how much of a performance impact that's having, but my bet is it's definitely going to be noticeable. Right, we'll keep going and we'll see what we can do. Okay, so scenes are composed of all of these kind of spheres, I guess. You have a bunch of random, I guess this is just a bunch of random sphere materials, and spheres are randomly placed as well. You have some glass stuff. You have 3 materials here, so 3. I don't know which scene we're actually running. Let's see, M scene type is default scene, so it is in fact this first one. Okay, sure. So again, you're creating the scene up, and then the renderer will eventually go through that scene and shoot all these rays. It will go to scene hit. We know scene is that hittable object list, so that will then once again SCD accumulate. I'm not exactly sure why you're using SCD accumulate here. I am not very familiar with this function, but this to me at the moment is kind of screaming out over engineering. Like, what I assume accumulate is doing is you're just passing in this kind of lambda here, and it will call this for each object in this range and then accumulate or sum up the values. That's what I think is happening. I would write this as a for loop because I think that would both make more sense and also will probably avoid like a lot of the overhead. But I'm not exactly sure again how that's all going to work, but I do see what you mean by you've kind of updated it more using all of these library features. Again, optional, accumulate. I probably wouldn't use any of these, to be honest, because what it's doing is it's adding a little bit too much abstraction for my liking to the actual mathematics and the actual data, which is exactly where we should be prioritizing this entire code base. Okay, so now that I'm more or less familiar with the code, let's go ahead and launch the performance profiler. So we're going to target CPU usage, hit start. Again, we're in release mode. Let's hit start, and I'm going to let it run for a little bit, especially over these spheres. And I'm really interested in seeing exactly where that CPU time is actually going. So if we go back here, hit stop collection, let's see if we can select a range that was after we actually hit start, which is this section over here. We've got a decent amount, like 10 seconds here of sample data. Let's take a look at what's going on. And it looks like there is no source information available. Why are you not like compiling with debug symbols or something? Release. Let's take a look at like linker debugging. Generate debug info, no. Maybe this is for like some performance optimization, but let's just enable that. And then let's also just double check here that I have no idea where this is. Debug information format. Yeah, let's just set that to like C7. And I'll go ahead and make sure that's done for the renderer. This is a static library, so it's not going to have those linker settings, but debug information format C7 compatible. And I think app as well. I'm not sure if we're going through app or if that's a different program, but just in case, I'll set it all to C7 compatible. Let's go ahead and close this session. And then we can just go debug and relaunch performance profiler. Okay, so I've hit start. Hopefully we'll actually get some debug symbols going here. All right, that's enough. Let's hit stop collection. Not sure if you can hear my computer struggling with this, but my goodness. Networking 98%. Why? Okay, so let's take a look at this. So this is the hot path, 86%, 51%. Again, it's all, so render a shoot ray is taking 97%. That's what I would expect from a ray tracer. Let's take a look though at what exactly is going on. So there's all of our source information. Okay, attenuation. Let's just expand that hot path and we'll see what's going on. SCD accumulate. 35% is spent here. And yet, so this is sphere hit. This is the mathematics. And these are all like below 0.2% of total time. In fact, this is 0.76%. But this is 35%. What is going on? Reduce op. So that's the function. That's the templated function we're passing in. So that's this lambda. What does that lambda do? Object hit. Yeah, which is sphere hit. And this is an if statement. That's the return statement. That's getting that optional value. How is where is all the performance going? What? I don't understand this at all, I'll be completely honest. I'm not sure how 35% of our time can be here. What's first? So we're dereferencing first, we're passing in a value. U first is, oh right, okay. So that must be, let's go back to here. That must be the actual object that we're iterating over. So that must be the sphere. Yeah, there it is, because it's that parameter in the lambda as well. Okay, I don't know why accumulate is so slow, but here's what we're going to do. The problem with this, the problem that I don't like is that, again, this is redirecting to some other code that obviously we didn't write. And furthermore is using this kind of lambda, which again goes here, but it's a little bit weird. Like this lambda, it's not showing me the actual details of the lambda for some reason. So in other words, it's not showing me what part here is slow, because again, I don't really see what's going on. Like I don't see why any of this would be so slow. But let's try and rewrite this as a for loop, because I want to actually see the profiler tell me what part of the for loop is slow, rather than just being like, yeah, it's this whole accumulate lambda thing. Because again, I honestly do not know why this is so slow. So where was that slow thing? std accumulate, this is, what file is this? Hittable object list, probably. Yeah, hittable object list. So let's go to hittable object list. And let's go ahead and rewrite this. So how would we rewrite this? Well, first of all, I want to do this in such a way that we can easily go back to the other implementation, so we can test the difference between them. So let's go ahead and copy this. And okay, so how would we do this? Well, we'd start off, and I'm going to write this in as simple of a format as possible. So I'm not going to use a range-based for loop. Again, I'm trying to make this as simple as possible. I've got that Clang format thing. I'm trying to make this as simple as humanly possible, right? Because this should be all kind of line by line, so we can see if retrieving some kind of memory is being slow, like what is taking up all this time. That's what I'm interested in. So we'll go through all this. So we need to get the object. So let's say, okay, so what is the type? The type is an std shared point. Again, I'm going to write all of this stuff out. So this is going to be a const reference of this hittable object. We'll call it object because it's this thing. So const auto is what we're taking in. So we've basically duplicated this here. I could have made this auto, but I'm trying to be explicit. So objects I. So we have the object, and now we just need to do this. So if temp hit, then object hit, and then return temp hit. So closest so far equals the value, return temp hit. Oh, that's what we're accumulating, I guess. What are we accumulating? std optional hit. So this is probably the initial value. So let's start off the initial value. Record. And then let's do hit record, return temp value. And what's a hit record? All of this stuff, set face normal. Okay, so if we've hit something closer, I guess we can just set record equal to temp hit. Otherwise, it's going to be temp value, which was the first parameter that we took in, which would have just been whatever we set it to last time. Okay, so I think we don't even need that. Okay, so if I'm not mistaken, if we hit something closer than the other thing, then we overwrite the value basically with this, and we keep track of what is the closest so far by keeping track of the distance of that ray to the thing that it hit. And again, if it's closer, then we override it. Otherwise, we don't. We just keep it. And then I guess at the end, we just return... Well, we return this. So at the end, I guess we would just return this record over here. So let's return that. And then let's get rid of all of this. Okay, that looks pretty reasonable to me. Let's just run it to make sure that like it works, I guess. And then we'll see. Whoa. Look at how fast it's running. What? Does this look the same as the other thing? Have I made a mistake? Look at how fast that is. "23 seconds. What happened? How is that 23 seconds? Should I take a screenshot? Like before and up? It looks the same, doesn't it? What on earth? Let's quickly run a profile over that. What? I mean, I have never used SCD Accumulate before, like ever. I don't think. I've come across it, but I've never actually written it before. Is it really that slow? Is there a bug in this MSVC library or something? What's going on? Why is it so fast now? And that's not even, this is still running on half my cores. But look at this. So where are we spending the time in now? Hittable object list hit still. Okay, so object hit is taking up 32% as you would expect, and then let's just expand that hot path. Sphere hit. Okay, this looks better. So you can see that we're actually, okay, so some of this optional stuff might be slowing us down a little bit. You can see it's taking like 3%. Maybe I wouldn't use optional as well. But you can see that we're more or less inside this function now, because we can see that we're calling hit and it's being called. And again, those samples, this is a sampling profiler. Most of those samples, 30% are ending up within this function, right? And then the rest, by the way, are probably also ending up within that function, but in a different stack frame. So really, they're all ending up within that sphere hit function, which is, again, what you would expect. Now, to take this a little bit further, I wouldn't use optionals here at all, right? Because what you're doing is you're saying that in certain cases, right, let's just return like an optional with no value. And then that way, obviously, back here, we can use that if statement that we had here, right? Well, we're still using it here. We can use this if statement to determine that it was not hit. So therefore, you know, whatever, let's not update the record, and, you know, because there was something that was closer, I guess, or whatever, or it just didn't work out. So we return optional here. We return optional here as well. Find the nearest root lies in the acceptable range. Sure. I probably wouldn't do that. And then also you're creating a hit record here, and then you're returning it packaged inside an optional. What I would probably do is basically bring out like a hit record like this. Maybe set some kind of like default value for T, like -1 or something. This returns an optional. That's fine, because obviously this isn't per pixel or whatever, I assume. Well, this is per object. Maybe this would be, maybe we don't want to return an optional here as well. But if we did, we probably could just check T. If it's -1, let's return, you know, a blank optional, however you even do that, which I guess is, well, you did that before, so it's just this. Otherwise, we'll return that record or something like that. And then we'll pass this record as the kind of, you know, target of this hit. So that way we don't have to create a hit record, copy it, do all of that stuff. It's already within this stack frame. And then also it means that we, you know, we don't need to return optionals or do anything like that, which seems to be taking up some of the profiling cycles that we can see over here, right? We don't have to waste all that time doing this stuff because we can obviously just, you know, we can just, well, return, I guess. We can make this a void function, and it would write everything into that hit record that we actually pass in, and in this case just not write anything, right? Because that's effectively what's happening anyway. So we could definitely, and then we wouldn't need any if statements, because this function would be the one doing the work. Because I guess from another kind of code, like looking through this code and this algorithm, another thing I don't like is you've got a bunch of if statements for stuff here, but then you're doing it again here. So then you're checking this if. Right? These ifs should almost, in my mind, be enough to say, okay, don't write anything in here. So therefore, we don't need branches within this function and other branches outside of the function at this level, because that's just like, that's just a bit unnecessary. So there's still a lot we could do. That's not even to mention the whole shared pointer situation. Because again, I wouldn't use shared pointers. Okay, so this code review is already dragging on, but let me know what you guys think of all of these proposals. If you want to see me implement this and take this project as an example and try and make it as fast as possible, remove the shared pointers, remove all this optional stuff, maybe see how much performance I can squeeze out, let me know in the comment section below. I will make an additional video where I go through and try and optimize this specifically. Maybe this code review series is going to become an optimization series, but let me know what you think of that, because otherwise I know that maybe not everyone's interested in the optimization part of this. And also I think we've got some pretty decent gains, if you know what I'm talking about. I mean, we went from like 7.5 minutes to 20 seconds. So I don't even know how that's possible. Let's maybe restore this to like what it was before. So this was an SCD optional. Let's hit F5. But yeah, that's like, I mean, this still, I think, could probably be optimized a bit more. It is still, in my mind, taking a considerable amount of time, probably for the reasons that I've mentioned. There's just a lot of like shed pointers and memory all over the place. But 22 seconds, man, from 7.5 minutes with using only half the threads, because I've still got like the divided by 2 there. I think that's decent. Okay, so let's quickly wrap up this code review. We'll see what else we missed and what we have to look at. Again, there's not even that much stuff going on here. I just like to summarize, I don't like the object-oriented nature of this. I think it's a little bit also over-engineered in some areas. I think that, I mean, you know, you've got like 10 years of experience, as you mentioned, with this. The code itself is very well organized. You definitely like, you know, you've made an effort to make it good. But I think, again, and you know, there's exceptions and all of this stuff, which is fine. Like in the, compared to some of the other stuff, exceptions are fine. I'll forgive you for that. Because that's obviously more of a personal opinion anyway. Everything looks really clean. Maybe some more comments regarding some things would be good. But to be honest, like this is pretty standard. This is like you making a projection matrix basically and setting up the camera. This is totally fine. Okay, so you're using some randomly kind of generated rays as well, which is again pretty typical, to be honest. Most of this is in fact math. Not sure why you're using SCD instead of GLM here. I don't know, maybe it's faster or something in some cases, but I would expect you to use GLM probably everywhere. Yeah, I don't really have too much to say. I mean, all of this stuff is pretty decent. Like, again, I don't have any negative feedback about the actual code style or the way you've written this. I think it's nice, but I would kind of reduce it a little bit more to be like, you know, kind of closer to the metal, so to speak. I would kind of reduce some of the abstraction and the fluff and the kind of hierarchies of object-oriented objects and, you know, heap allocations with like smart pointers and optionals. And like, I would reduce all of that stuff. I would kind of focus it more on the math and focus it more on the memory and the way that the CPU is processing this. I mean, honestly, like I like this code. I would be happy to take this. Maybe I'll do it myself with the ray tracing in a weekend series that I was talking about. But I think this is a great case study for how we can take some over-engineered code that is running slowly, as we saw, and make it as quick as possible. The other thing that would be cool to do, as always, is to use a GPU to do all of this computation, because that's obviously going to be much, much faster, and you won't have to manage some kind of thread pool with only, like even on my computer, 32 kind of threads running. You could have like thousands on the GPU running in like fragment shaders or compute shaders, right? That could 100% be done, and that would be way, way, way faster. So that could be another way that you could obviously extend this. I'm getting motivated hearing myself like explain all of this. Now I want to write like some kind of GPU based, very, very fast ray tracer. But anyway, hope you guys enjoyed another ray tracing code review. Let me know what you guys thought about all of that. But of course, I think the way that we looked at this compared to the other ray tracer that we looked at was very different. So I hope that this was helpful for you guys. Hope you guys enjoyed this video. If you did, please don't forget to hit the like button below. As always, you can send in your code to chernoreview@gmail.com. There will be some instructions in the description below. Whatever it is you're working on, if it is interesting, if you need some help, if you think it'll be a good learning example, or you want some guidance as well, feel free to send it in. I do get a lot of emails, as I mentioned, but who knows, you might just be the one. Thanks for watching, guys. Don't forget to check out Skillshare using the link in the description below, and I will see you next time. Goodbye.